Welcome back to our video module on quantum mechanics. We've been looking at the infinite square well, and we've been able to identify the form of the solutions to the wave equation within the square well. In addition, we've also been able to understand the meaning of energy within this equation. And of course, the beauty of these solutions is that they tell us not only a snapshot of what the wave equation is like at any given time, but they tell us how it evolves over time. All we're missing to get an actual solution is an initial condition. How does the wave function start? So for instance here, I've drawn our potential profile. We'll assume it's an infinite square well. And in blue, I've drawn the profile of the wave function at time equals 0. My challenge to you is, how do we identify the equation of this wave function as it evolves in time? Today, we're going to be looking at superposition and the basic steps we take to be able to solve the types of problems that describe wave equations as a function of time. So the first thing we might ask here is, what are we even trying to do here? Well, if we can recognize that our waveform is really some summation, some superposition state as a function of time. So we saw this earlier when we identified the time-independent Schrödinger equation, that if we have some state of a wave, it can be represented by simply a sum of time-independent solutions. Well, this can be really useful to us because in this potential profile, we have phi of t and we have c of x. All we need to do is identify the coefficient in front of them. In other words, how do these states add up? Remember that a superposition state of a whole bunch of odd sine waves lead to something like this. Now, if only we could figure out this Cn and the details of the mess, we might be able to actually come up with a solution. Well, first, let's figure out what that waveform is at time equals 0. And in this case, I always like doing rise over run, in which case you get 2ax over a. But remember, this is only for x values that are greater than 0 and less than a over 2. Likewise, we have a negative 2ax over a for all x is greater than a over 2 and less than a. Well, what are we going to do with this a? How do we determine this initial condition, how far vertical it is? We've had this question before, and it's a normalization question. Basically, at time equals 0, we know that the probability of a particle be between 0 and a is 1, which means c star times c, the integral of that equals 1. It sometimes makes it a little easier to see that this is symmetrical about a over 2, so you could just integrate from 0 to a over 2 of 2ax over a, and just set it equal to 1/2. Let's put a square in there. And with a little bit of calculus, we come up with a equals root 3 over lowercase a. Hence, we've normalized our curve. So now we can get to the fun part. Now we can take a look at our general equation and try and find ways to combine our solutions, either C1, C2, C3, C4, all the way up, so that we have a form that answers this initial condition. The trouble is here, Cn. The trick is nicely dispatched by using Fourier's trick, where we take the integral conjugate of the initial wave function times the wave function of a particular state. This basically tells us how much of this particular state contributes to our initial condition. So what would that look like? Well, let's try the first one. C1 equals the integral, and what we'll do is we'll pretend that we're only looking up to a over 2. Because the initial wave function is even, we decided to only look at the left half. As a result, if we want the actual result for C1, we'll have to multiply our answer by 2. If we go through the calculus, we see that this equals 4 root 6 over pi squared. And if we were to actually, instead of doing C1, if we were to instead do C as a function of n, 1 over n squared 4 root 6 over pi squared times sine of n pi over 2. Fair enough. Well, how can we make sense of this Cn? Well, first we notice that as the energy level or as the end state increases, the contribution of each of those particular states decreases as n squared, which means the profile that's going to contribute the most to right here is going to be the ground state. And we kind of had a feeling that was the case just by looking at the shapes. The second thing that's interesting is when n, right here, is an even number, this whole thing's going to go to 0. In other words, there is no contribution when n is even, C of 2, for instance. Now, if we look at if we look at this as saying like the origin is at a over 2, we notice that this stationary state is an odd function. And if we compare that with our starting place, if we pretend there's an origin about the center, we notice that we'll want an even function should be contributing. So we had an intuitive feeling of that in the beginning when we said, okay, we expect the even stationary states here and here to contribute, and we don't expect contributions from the odd. And when I say even and odd, I mean about the center of the infinite square well. Now we're ready to return to our original question. Basically, we said that the overall wave profile is going to be represented by some summation of stationary states. We have a solution for Cn, we have a solution for the actual states, and we have a solution for the time dependence of the states. So we can write this all out. And while this is quite a handful, we simply need to remember that we're looking at the sum of Cn times the x dependence of the wave equation and the t dependence of the wave equation. In this way, we've been able to use our initial condition, basically a snapshot at t equals 0, to identify how the wave functions for all time. In summary, if we're given some initial condition and we want to find the behavior of the wave function over time, we have several steps to follow. First, we'll identify the initial conditions, recalling that we were given this basic shape, and then from there we were able to identify the general format here. Secondly, we were sure to normalize the initial condition. This allowed us to make sure that the probability of a particle being between 0 and a is in fact 1. And it allowed us to identify what this coefficient was. 3, before jumping in and doing all of the math, we used some of our intuition. In this particular problem, we looked at the profile about a over 2 and saw that we had an even profile, as the left and the right were symmetrical. Therefore, we knew that we'd get all of our influences in the superposition states from likewise even superposition states, and we'd get no contribution from C over 2. Now, fortunately, in this case, when we calculated our CNs, it wasn't that big of a deal, odd or even, but that might not always be the case. And in this case, it allowed us to assume when we did C1, C3, C5, that the actual coefficient was double the coefficient that we got from 0 to a over 2. In other words, we knew we'd get the same on the left as the right, so we could double our coefficient. Our fourth step was to identify the coefficient before each stationary state as an indicator of that stationary state's contribution to the overall wave function by using Fourier's trick. Finally, we were able to use the superposition characteristics of the time-independent Schrödinger's equation to identify the full characteristics of this waveform. Hopefully this quick view at a rather simple problem gives you the structure and the insight that you need to deal with whatever types of initial condition problems come your way when you have to identify the full wave equation as a function of both time and position. Thank you for joining me for this video, and I look forward to exploring more with you next time.